All right, next up we're going to do the AI Roundtable. That's going to get started right now. And so I'll turn the floor over to our moderator, Chad Hart.
Great, thanks Travis. So I was up here yesterday. Hopefully most of you know I'm not going to spend a lot of time on me. But I was going to ask each of the panelists to talk a little bit about their involvement with machine learning and artificial intelligence and what they're doing. And I probably should do the same for myself. So I had been doing a lot of work with speech analytics specifically and playing around with a lot of computer vision stuff. And I realized there wasn't a whole lot written out there on how AI and machine learning technologies apply to real-time communication. So I actually started a new blog and been focused on that quite a bit. You can check that out at cogint.ai. And then in addition, I found actually there's a lot of people that were interested in this topic. So I got together with Sai Levant-Levy, and we decided to put together a market research report, which we need to finish in a couple days, up to 90 pages. It'll probably be quite a bit longer than that. So I've been spending a lot of time on this topic in the last few weeks. Talked to more than 40 different companies over the last 6 weeks or so about this topic, and I'm looking forward to hearing what the panelists say. I will say, if anyone's interested in a free copy, at least the executive summary, we are running a survey right now where you can just input your usage and what your thoughts are around machine learning and AI and real-time communications applications. We also are giving away, 5 $100 Amazon gift cards, and it's about 103 participants right now, so your chances of winning are pretty good. But enough with that. So I do want to jump in to the topic at hand. Adding artificial intelligence to all the telephony stuff that we do every day, and there's certainly a lot of hype around this, and a lot of mystery, a lot of magic. A lot of people just you add some AI, and all of a sudden you get this robot who can make automatic calls. I did want to emphasize. And we'll go through as we go through the panel, but there are a lot of actually practical, real-world use cases that are being done already, and a bunch more that are actually pretty practical to do, but that aren't being done just yet or are just emerging. The first one, the biggest one, is really speech analytics, and this has been going on in call centers for quite some time to monitor agents, to verify compliance. Doing translation type applications, analyzing calls, that sort of thing. It's all very common. This technology here is pretty mature and actually getting very inexpensive to run. Voice bots is a whole nother huge area. So we've heard about Dialogflow a few times here. That's certainly one, but there's other voice bots out there. But certainly there's big opportunity here to replace crappy IVRs with something that's much more human, much more realistic. In addition, there's a bunch of companies out there doing in-call assistance and that sort of thing, focusing on conference calls and meeting experiences. Right. Next, we turn to computer vision, right? So actually, we saw, Sebin had a good example where you drop out the background and put something new in. The funny hats examples, or putting mustaches on people, are pretty common in social media. But even beyond that, for a more business context, there's Microsoft and Cisco have shown demos actually where you do facial detection, identify the speakers and show who they are, that sort of thing. Gesture detection, identifying things. I mean, there's also Travis and the Microsoft demo showed object detection to be able to identify things for remote service, remote support. So a lot of really exciting things there that people are actually doing now. Maybe it's not super wide scale, but I think are within reach of everyone here to start doing. All right, and the last one is just optimizing real-time communications and actually improving how things are sent. Right, so there's a lot of hard-coded algorithms today for dealing with things like congestion control or simplistic ones. There's a lot of opportunity there for improvement and potentially use of machine learning for that sort of thing. Not to mention, there's a ton of route optimization where some of these algorithms might be used already. So maybe rather than me introducing the panelists, it might be good just to save some time have each of you introduce yourselves briefly. Talk about how you're using machine learning, your application use case, and then we'll dive into some questions and then take some audience questions. So why don't we go just from my side down. James, if you want to go ahead and start, please.
Hello. Yes. Yeah. Okay. So, so I do two things. I started the Roger Penrose Institute, which is the English mathematician, physicist Roger Penrose. And in that area, we fundamentally believe that there's a difference between human and artificial intelligence. And so humans are able to do things that artificial intelligences are not able to do. And where do you see that happen? Well, you see that happen where a friend of mine has a Tesla, it's in his garage, he can't drive it out because it thinks it's too close to the bars, the entrance of his garage. So he can't actually get it to drive itself out. So he has to do it. So you have these sort of things where an AI can't just look at a situation and go, okay, it's sort of a bit tricky, but I can get through it. And really complex stuff like conceptual things. So humans are quite good at conceptualizing really bizarre ways, and AIs just can't do it. So, for example, Noam Chomsky gives this example of New York burnt down, but it's okay, it was rebuilt in California. Right? And you think about, well, so what is a place? What does it mean to be New York? And so on. So we listen to that phrase and go, oh, okay, that's quite, we understand it. But computers find it very difficult to understand slightly abstract things like that. So on the other side of what I do is I've started a company called Sen AI, and Sen AI tries to look at questions that are asked of an AI and decide whether the AI is going to fail. And if it's going to fail, you vector it to a human being in real time. So that's the real-time communications that we all know and love. And so that can be applied to language or backing out your garage or whatever. It's just the ability to make a decision about a problem, decide that's going to fail, and get it over to a human being as quickly as possible to intervene. And so those are the two things I do.
All right, thanks. Verona, CallStats gave a talk on this, but maybe you can give a recap.
Yes. So when we started CallStats,
You might want to check your mic.
See, human intelligence is so superior to artificial intelligence.
Has its own failings too.
Actually, it would have detected I was trying to speak and it was turn it on by itself. And I have to do like 5 steps before it turns on. Yeah. So yeah, we did do a talk, and Binoy gave a talk yesterday. So when we started CallStats, it was a big data play, and one of the things that we knew off the bat was that we would want to use the data to do something smart. But it did take us a fair amount of time, like 2.5 years before we could even leverage the data in any meaningful way. First, because the data that was coming out of the browsers or wherever we're collecting it was tainted. It was not always reporting things correctly. So things that we thought were being measured appropriately were not being measured. So it took us a while before we could actually get things to work. But one of the things that we wanted to do from the beginning was to optimize networks, to use them more efficiently in whatever way would be feasible with the technology that would be there. So initially when we started, there was SDN, NFV, which is we call it self-driving networks, but software-defined networks, and network function virtualization, which means that you had all these components that were available and were software-driven, so you could manipulate them. And so we started with simple problems like my background was in congestion control, so we used AI and ML to look at single streams and see how we could improve those streams in terms of both bandwidth estimation or latency reduction and so on and so forth. You're trying to optimize in the sense of getting highest quality of video and audio across a particular set of paths. The second thing we wanted to do was, as soon as we did that, was to figure out we all have smartphones, and our smartphones are capable of sending video over Wi-Fi or 3G, and to be able to detect which one would be better, both in a localized way and the other would be historical evidence. So for example, I'm at home. Do I need to reconfigure my apps to do a certain thing? And when I go to work, can they learn by experience, right? Because we learn by experience as well. And sometimes we don't. For example, I did not know this was turned on or off, but the machines are really good at making sure that they understand context really well. So that was the second thing. And the third thing that we started to do was look at networks as they're built to see what are the deficiencies in the networks and where we can plug holes. Because a lot of the times what we do as network engineers are look at data or look at feedback from customers to see like what the holes would be. So for example, if something's happening in a certain place, like for example, I don't know if you were monitoring like all the network traffic that was being reported during the World Cup that was just a few weeks ago, and there were like people who were showing like network traffic, and they would say, "Oh, this was the game," and like you can see these network traffic bumps because whenever the games would be on, you could see media traffic increase. And then there were people who had pre-provisioned for this, right? And then there are people who had not anticipated it and were pre-provisioning after the fact, like after the first few games. So these are things that could be improved just because if there are machines that are like capable of, like we already know how to like horizontally scale stuff. We know how to like reduce the reduce when the load is lower and so on and so forth. But some of these things are actually still under human control. Netflix is a very good example where they use chaos monkeys and so on and so forth to like go one step further than whatever. And I think we can go one step further with some of these tools.
All right, great. Thanks. Michael, would you like to go next? Same thing. Now it's automatic.
Yeah, so my name is Michael Schloh from Bennewitz. I have a laboratory in Europe, and what we do is a lot of hardware. Now, this is not obvious where the relevance is for a data center centric signaling and media system like the ones that we're talking about. We're doing a lot of signaling here, media and multiplexing of streams, as we saw with 7Do's wonderful chroma key application. And when you start developing hardware, which may go out and never come back and be difficult to manage, we discover problems and that are difficult to anticipate, like the Mirai vulnerability from a few years back. And this is all bringing back buzzwords like IoT, but there are things like signaling and media involved with webcams and so on. And the hardware for these types of things made by people like me do benefit from AI and machine learning as well, which I consider a workflow being the learning of that information, the building of the data sets, giant data sets, which are then leveraged in order to discover and search for patterns. You find those patterns, and then you can do something with those data sets and the patterns you've discovered. You can execute and discrete algorithms, for example. And for me, this is the way I think of AI and machine learning. For me, it's relevant because as a hardware maker, I want to use AI in order to deploy and manage these nonlinear scaling giant amounts of hardware devices which are going out into the world. Just like these NFC badges, the ones which I created, NFC can be put just about anywhere because it's so low cost. But once you deploy that and maintain and keep it up to date and analyze it from afar, you can't do that on a human level anymore. You need some machine assistance and some AI for that. So that's the reason I'm here.
Great, thanks. And Travis, would you like to?
My name is Travis Cross, and most people think the current round of this AI boom started in about 2010, 2012 when the guys from Canada showed up at the ImageNet competition and just blew everyone away. But for me, it started a few years earlier. Around 2005, spam was becoming just a huge problem on the internet, and there were a group of us who would get together and talk about what we're going to do about this problem. In fact, Paul Graham, who's now most famous for starting Y Combinator, at the time held these plan for spam camps, these plan for spam conferences, single-day conferences, and he would hold them up in Boston in January. Now, I don't know if you know anything about Boston in January, but it's pretty miserable there. And the reason why he held them there in January was he only wanted serious people to show up. He didn't want to hold them in Las Vegas or somewhere fun that people might want to go. So all of us people who really cared about spam would show up in January in Boston. And what we figured out after a few years was that the only way to solve the spam problem was not blacklisting IP ranges or other heuristic solutions, but actually to look at the content of what's in that message and use what, by our standards today, was primitive artificial intelligence to look at the email in the same way that a human would and try and work out, is this something that a person wants to look at or not? And so what really solved the spam problem was working on statistical machine learning techniques that allowed us to force the spammers to have to structure their messages in a way that they became less effective. So at that time, I was working on that kind of spam filtering. And then in recent years, I've been working with a team of people to do research on machine learning for proprietary trading applications in the finance sector. But then we're also looking at how those same techniques can be applied in the cybersecurity sector to detecting threats that are coming into networks and then automatically responding to them. And that has a lot of applicability into protecting real-time communications networks and many of the same systems that we work on.
Great, thanks. So now I'm actually going to sit down and we'll run through some of the questions here, and we'll take some questions from the audience too. But maybe before we dig too deep, we probably should do some definitions here. I mean, it's called AI. There's a lot of hype around AI. Machine learning is probably the stuff that developers and people in this room would actually have to do. I'd like to first hear like your opinions or your definitions. How do you define AI versus machine learning? And this time, actually, why don't we start with Travis, and we'll work towards me.
You know, I think today the words have merged so much that they are synonymous that I'd almost say that machine learning is the term that's used within the field for the problem, and that AI is the term that's used as a marketing slogan. But strictly speaking, they are distinct, with AI being the pursuit of intelligence as an abstract concept in an artificial form. So any technique that one could use to try and generate intelligence, however we define it, in some sort of way that we can create that. Whereas machine learning, strictly speaking, is the act of using a particular but very broad set of techniques to learn how to solve problems by some sort of reinforcement or training or back propagation, some system of working out the right answer with a machine.
Yeah, Michael, I mean, how do you see it when you're in a data center? What terms do you use there?
I'm using the term machine learning almost exclusively when I talk to colleagues. I'm not with Intel, but I'm an Intel innovator. So Intel is the original developer for OpenCV, which is an open source project today. It was Intel before, and Binoy is a different one. So when I'm talking to colleagues at Intel, we're just speaking about machine learning. That four-step workflow that I talked about before, the machine learning and the building of data sets, and then the searching of patterns and the executing of algorithms. Those building of data sets is so crucial to all of this, to this topic that we're talking about, that without a data set, there's not much else that you can do unless we jump into the future with quantum computing or something like that, which I have no idea. But you need the data sets, and the thing that precedes data sets is the machine learning, right? So for me, that's the key phrase. And if I were speaking to, well, a child or a person that is not so influenced by computer science or knowledgeable, I would speak about maybe AI, artificial intelligence. That's when a robot can speak to you. That's what Kit the car did, and so on. For me, that's artificial intelligence.
Okay. Or investors.
Yeah. Well, Varun, your colleague Binoy did a talk on AI yesterday. I think probably on the marketing side you use AI. How about internally? I mean, how do you define those two terms, or do you make a differentiation?
Yeah, actually, for a long time we didn't call it AI or ML, because initially we just wanted it to be like statistical measures. Now this could be like through one or more techniques. So initially, because of the investors, and we were not fundraising, so we never used it. But over time, as we have started speaking more to investors, it tends to be that you use them interchangeably. If you say ML, they say AI. You say AI, they say ML. So it's like, well, whatever. Let's just use something that can be. So it's more like a marketing term. But when we started initially, it was all about statistics and finding out what techniques would work for us. So it was either k-means clustering, LSTM, ARIMA.
Yeah, and I do want to talk about some,
Yeah.
we'll get a little more specific next.
Right, and then when we started to use like CNNs and then most recently ANNs, then we start to like see the whole gamut and spectrum of things. And people also are changing. So initially we had more mathematics people in the team, and now some more ML people are on the team. So they, of course, correct us or correct each other all the time about everything. So
yeah. So and James, your last one, you didn't mention you're an author. You've written a book on the topic of AI,
yes.
and you, but from the looks of your website, look around, it's more machine learning oriented type stuff you do. So how do you define those two terms, and for you, how do you use them in your different spheres of or domains that you work in?
Well, I mean, I wouldn't define those two terms. I mean, the interesting thing for me is you go out into the foyer there, and there'll be some artificial flowers and some real flowers, right? And we get the same pleasure from them. They have the same utility, yet one needs to be watered and one doesn't, right? So is there a fundamental difference between artificial intelligence and real intelligence? Is there a thing called real intelligence that artificial is not? And, is artificial intelligence a thing that needs defining? Or is it just able to do anything that we broadly call intelligence? What's the artificial for? So obviously I have some very strong views on that, which we'll go into over a beer later probably. But yes, that for me. And then once you're in artificial land, anything that looks vaguely intelligent, whatever it is, that does something that you and I would do with our brains is doing an artificial intelligence job. Even if it's just choosing one item or another.
Okay. Well, next I would like to get, since we do have an audience of open source developers, out there who want to learn about some of the stuff. I do want to talk about some of the specific algorithms and mechanisms and ways of doing this. So maybe, Varun, I'll let you start off, and how much of what you do is just a simple statistics and linear regression versus some of the other techniques, and maybe you can talk about neural networks and some of those approaches too.
Yeah, so like the initial problem when we wanted to tackle, which was really hard because the labelings was all off, was Wi-Fi 3G, right? So we know as humans what is Wi-Fi and 3G, and when we look at, like when we choose them, we know what we're choosing. But when when an application uses it, sometimes the application doesn't know what it's doing, just sees IP addresses, right? And what we tried to do at that point was sometimes, and there are networks out there where people tether, right? So you see Wi-Fi, but it's actually 3G. And then there are things that are like 3G, which is on top of another 3G or some weird stuff happening. So we started looking at patterns and clustering them just to identify if they were Wi-Fi and 3G. And then you would do it by clustering and looking at, all these things behave somewhat similar and some things behave differently. And then there's this whole slew of things that are in between. So there's clustering initially for some things that we were doing. There's LSTM for some of the stuff that Binoy showed yesterday, like, for example, finding the needle in the haystack. What he showed was, of course, a single metric. What we, of course, are doing is more involved, like taking hundreds of metrics and then looking at patterns and trying to see if there's correlation or not. And sometimes you don't even know what is correlated to, because we as humans can reconcile stuff when things happen the way we think, and when they don't happen the way that we think, we dig in a little bit more and say, aha, it can happen this way as well. And sometimes it's really hard to build systems that can do that off the bat. So sometimes what we do is we just let it do stuff. And in those cases, we've tried to use ANN and say, maybe it'll tell us something intelligent, and then we'll go and dig around and see if there is something that we should be looking at. So that's our play of reversing it and saying, go find patterns, then tell us these patterns, and then maybe we'll try to figure out if these patterns make sense or not. Because I think humans in general, small patterns we're not able to see. We're able to see stock patterns. So the machine's really good at that, to finding these subtle things and then bubbling it to us. And I think that was really surprising to invert the problem.
Yeah, and you're, I'll let the other panelists comment in a minute, but I mean, so you're implementing the algorithms yourself, right? Using something like TensorFlow?
Yeah, so we start with TensorFlow. We use like the stuff in Python when we're working with it while we're trying to figure stuff out. And then when we go into production, we use Golang, and like they had a module that they released last September, which helped us a lot because before that we were like doing all this stuff in Golang by ourselves. Then they did this module, we were super happy. Then I think Amazon came up with Slaymaker or whatever it's called. And we've not played with that because we were already in production at that point. But this is something that we would look at as well.
Okay.
So
and those are all open source?
Yeah, like we use as much as possible. And then the algorithms ourselves, like some of it is implemented by us, some of it is available Python, not in Golang, then that's a little bit more tense situation for us.
Okay. Well, I want to put the other panelists too. Maybe we can talk a little bit about one. I guess what are some of the specifics of what you do in your implementations, in terms of if there's specific algorithms or libraries, frameworks that you're working with.
Well, okay, so I'll just say that I've worked with OpenCV, but not in the manner that you've been doing so much in production. So I've been teaching classes and so on, and a lot of experimentation and research.
Okay, yeah, and OpenCV is well. So one of the things I did in my Cogent AI blog is I looked at some of the top machine learning frameworks and libraries. OpenCV ranked extremely high, and especially for computer vision type stuff. TensorFlow overall by far beat everyone, and Google's putting a ton of is putting a lot of money and time and marketing into that, and education resources. And there's others like Keras and Cafe, and I mean there's a long list of them. Actually, depending on what you're looking to do, if you're looking to do speech analytics, or transcription, like Caldi is a good framework out there for that.
Yeah, Google has some very interesting and very simple speech analytic applications as well in their frameworks. So we've been using that as well. And Intel is pushing towards Vino. So it's just something that I haven't. It's so fresh that the innovator program is encouraging use of Vino instead of OpenCV or whatever else. There was something in between as well.
Okay.
It's always shifting.
Yeah, maybe on the topic of Intel real quick too. I mean, Intel has a couple chip efforts to do some of these things on chip. So I played around with the Intel Movidius chip. I don't know if you've seen those at all. More intended for end user devices, sort of thing, but where they actually can run your machine learning locally on an optimized chip for that, so it doesn't burn through all your CPU, and you can do things more. Have you looked at anything like that or any other? I mean, you must also get into GPU acceleration type. Maybe you could talk a little bit about that.
Yeah, this is a rather big topic because, first of all, the Movidius is exactly what you say. They're kind of pulling away from the cloud-based AI and trying to do things more locally, and keeping things internal to a network or inside the edge of the network.
Yeah, edge AI seems to be the buzz for that, right?
And this is appropriate for some things, line detection, and some more simple things where you can either store a set of data, or you're not exchanging giant amounts of data. When I do a workshop, when I teach, for example, using these speech analytics applications or OpenCV, is that we do have a set of Intel hardware. We haven't been using the Movidius, but we've been using, for example, the NUC, the new unit computing, I think is what it's called. There's a couple other pieces of hardware now that they're doing with Up Squared is one of them, which are nice boards because they've embedded a FPGA framework on there, so it's very good for graphics. On top of that, not just graphics, but the type of things that GPU kernels can give you. You can do your own application on that and do some cryptography as well. And they have integrated as well some high-powered GPUs. So all of that together gives you a bit of AI and machine learning inside the network edge. And then in our workshops, what we do is optionally send that out to the cloud. So we use Google services, for example, to identify speech patterns and to do text to speech or the other way around.
Yeah, so in the Google, you're just using the Google Speech, their public API, because their APIs.
Yeah, I'm not sure how many there are, but we're using a rather simple one because our workshops are 1 day or even a half day long.
Yeah, and Microsoft presented a bunch earlier too, and probably should point out. I mean, if you want to build all this stuff yourself, I mean, it's a little bit involved, but you can do it like RunZone. If you don't want to do it yourself, then there's these public APIs, from all the major cloud vendors, and there's a bunch of startups out there too that make it pretty easy. But maybe I want to give Travis or James, if you want to talk a little bit about.
I have a question for Michael.
Yeah,
if you don't mind.
Go ahead. Yeah.
So I mean, if you're working with the Intel guys, have they let on how concerned they are about this NVIDIA thing? Because they've allowed NVIDIA to become this huge data center company by virtue of how effective the NVIDIA cards are in training. And now there's this also the competition from Google with the Google TPU version 2 and all these things. It seems like this massive missed opportunity for Intel to extend x86, where they tried with the Knights Landing and their various cards and basically have failed to get a foothold in that market. Have they communicated at all about their direction or how concerned they are there?
Well, you're speaking of graphics, are you? GPU processing?
Speaking of the compute needs that machine learning brings to the table in terms of training machine learning models, where basically everyone in the field is using these NVIDIA graphics cards and building out data centers of these NVIDIA cards, and creating this, huge multi-billion-dollar, valuation for NVIDIA that is valuation for NVIDIA rather than valuation for Intel in a market that Intel has always liked to dominate, which is the high-end compute market.
Yeah, no, I can't say that directly I've heard information about that or a course of whatever they need to change in order to address that problem, a roadmap, if you like. I don't have special information for that. Isn't that too bad?
That's too bad.
Yeah, I mean, the problem with most of the chips at the moment is that they are old-fashioned graphics chips. And an old-fashioned graphics chip is designed to basically modify this image and change it in some way and compress it and so on. And it will work on every pixel in parallel, which is great. So you assume that you take that and work on every pixel in parallel and work on every weighting of a neural net in parallel. Sounds plausible. The problem with a neural net is that once you've trained it, once it's gone through its processes, something like 95 to 99% of the multiply accumulates and multiplied by 0. So this enormous, great big chip, and the NVIDIA chip is like the size of the palm of my hand and consumes what? Hundreds of watts?
250 watts.
250 watts, right? The vast majority of all of those gates flying around, flapping around, is doing nothing. It's multiplying by 0 and sticking it into and adding 0, right? So I think there's a big. I mean, it's way away from being optimized at the moment.
Well, I mean, to some degree, that can be addressed by software optimizations that people have applied to do the calculations in a way that recognizes that sparsity that you're referring to. So that's where some of the model compression comes in. But if you make a chip
to do that,
right,
you'll spank it, right? Just like the guys that have done the Bitcoin mining. You do an ASIC that does it, that's specialized in it, and it just destroys the competition. So at the moment, we're just reusing old-fashioned ideas for a new thing. So I think there's some big revolutions around the corner.
And I mean, the other hardware thing that's a problem is that not only do you have the sparsity, but you have the fact that every time you're doing a training epoch, you're having to reload all of your model parameters. So you're always pushing your model parameters in and all of this data.
Yeah.
And so the thing becomes I/O limited. And if you compare that to what we know the brain to be doing, it's just so ridiculously inefficient, because in the brain the model parameters are there all the time. There's no I/O limit of getting them in and out. They're just there and they change.
Quick, how many people here actually have done any type of machine learning training, whatever? Only a few. So I think actually, Travis, could you walk us through what does a machine learning pipeline talk? What does it look like? How does it work? Can you talk about training can you walk everyone through like the process for a neural network? Maybe explain what a neural network is, and then walk through the process of how you train one.
Sure. I mean, a neural network is like the brain only by analogy. It's the same as you might say that flying on a 747 is like a bird, but only by analogy. They're very different things. They just share a few fundamental concepts. And the fundamental concept is that you have a network of very primitive operations. So in the normal domain that we work in computing, we think of adds and multiplies and if statements and NOR and OR and XOR and all these things. In a neural network, all of these things become fuzzy, kind of like our brain. They become floating point operations that get to the right value, but only by a highly dimensional floating point calculation. And we implement that floating point calculation on our traditional computers using our traditional operations, but what's happening in the neural network is happening at a different level. It's happening at a level above that. And so you have this network where you start by feeding in data, and then it passes through these layers, and that's where the term deep learning comes from, is that we added a lot of layers to this pipeline. And so there's these layers where you're connecting all of these operations together. And the principal component of a neural network is that you have these interleaved layers, which are basically multiply, accumulate, and then a thresholding operation. So in a modern neural network, that thresholding operation is very simple. It's called ReLU, and basically it's just an operation where if the value that results from the multiply accumulate is less than 0, then we propagate forward a 0. And if it's greater than 0, then we propagate forward that value. So it's a linear function above 0 and is a 0 function below 0. And so that thresholding is called an activation function. So we have multiply accumulates of all these floating point values, we do a threshold operation, and then we repeat layer after layer of this. And if you're thinking to yourself, how does this generate intelligence? Nobody has a great answer to that question. That's an open area of research, but it actually works. And that's how the image recognition and text-to-speech and ASR and all of these cool technologies work, is by layering together these functions. And the way that this is trained is that you take what you want to figure out. So you take an image of a dog, for example, and you feed it into this network that's then going to take each of the pixels and do this, typically a convolutional approach to a neural network where it scans across it, multiplies and accumulates, thresholds, does this forward, and then you structure the network so that it gets down to an answer. Like, let's say you want to decide whether it's a cat or a dog. So the architecture of your network will come down to just 2 nodes, cat or dog. And maybe you'll get 95 for dog and you'll get 65 for cat. Well, then at the end of the day, since you know it's a dog in training, you'll then feed backward in the network to tell it, all right, we know it's a dog, you should weight it 0 for cat. And then you adjust all the parameters, working your way backward through the network just a little bit, just a touch, so that it makes it more of a dog and less of a cat. And then you repeat this operation millions of times, ideally, so that at the end of the day, for all the possible examples you could show the network, it's likely to say that a picture of a dog is a dog and a picture of a cat is a cat. And it's easy to get to memorize that. Like, if we could show it all the dogs and the cats in the world, it could just memorize all the answers. But what we're interested in the networks is the idea of generalization. The fact that we can show it some dogs and some cats, and then we can show it pictures of other dogs and other cats, and even though they're at a different spot in the frame, or they're a different color, or maybe they're a slightly different breed, that this network, all of these floating point values, will have somehow intuited the general idea of what is a dog or what is a cat, what are the important qualia of those, what are the important qualities of those animals, and that it will be able to generalize and get to the right answer. And that's the context in which we call a network intelligent for this supervised learning problem of deciding, is it doing the right thing in general and not just for the examples we've showed it.
Yeah, I know you have I don't know if you're covering this in your talk tomorrow. You have on this topic too. But I mean, does anyone else have anything else to add or expand on that you think is helpful, audience here?
This is classification.
Yeah,
so
that's a supervised learning problem.
It's a really, really rich gold seam, right? Because so many things can be turned into classification problems. I saw a virus detection company, and what they do is they take viruses and they make them look like images, and then they look at code that isn't a virus and code that isn't a virus, and they train essentially an image recognition piece of software, and it can now tell virus software from non-virus software. And I went to a startup competition. There were like 100 startups, and everyone got up and did a classification. I have a farm. I look at the field and I see where it needs fertilization. I feed that into an AI. It determines whether this is a good farm or a bad farm, classifies it. So classification is extremely valuable since we make digital decisions in terms of investing and going on holiday. And, you know, we need to decide, do this or do that. But most of the AI at the moment that we're getting is this classification AI. It's not very good at deciding what I would want to do next or conversing with us, which is still quite primitive. It's very good at saying whether I've said yes or no, or cat or dog, but not whether in context that makes sense.
Well, the thing is that once you get really good at something, you figure out how to turn other problems that previously were not classification problems into classification problems. So for example, my favorite example of this is AlphaGo, the DeepMind Google team that conquered Go. The way they did it was essentially, okay, so typically in machine learning, you have at least 3 categories of the field. You have supervised learning, that's where you know the right answer. We have a bunch of pictures of dogs and cats, and we want to figure out, you know, we want to get a network that can recognize dogs and cats. Then you have unsupervised, where you got a bunch of pictures of all the things, and you don't have labels for them. You don't know what all the things are. And so you just want to give it all the raw data, and you want the network to somehow work out something meaningful from it, even though you can't tell it the right answer. And then you have reinforcement learning problems. These are things like playing a game, where if we don't know the perfect way to play Go or to play chess or to strategize in war or to do any of these things. We just know what outcome we want. We want it to win. That's what we want. We want it to win. However it gets there is fine by us. And so typically these game-type problems have been seen as reinforcement learning problems. And we as a community of machine learning practitioners and researchers are not very good at reinforcement learning problems. There have been some great advances, but that's still the kind of trailing piece of the field along with unsupervised learning. Well, what the AlphaGo team did is they turned a reinforcement learning problem into more of a supervised learning problem via a neat trick. So that essentially their Go program is an image classifier, and they worked out a neat thing using something called Monte Carlo tree search so that they could use the process of playing the game Go itself to come up with the labels. And then by making those labels really good, they turned it into a classification problem. And so at the end of the day, the way that AlphaGo plays Go and beats humans is because it's seen a ton of examples where it knows the right answer to, I'm looking at this board, what is the best move? And it makes a snap judgment. And so that's why when AlphaGo plays Go, it actually looks through many fewer possible futures than 1996 Deep Blue. If you remember when IBM beat Garry Kasparov at chess, that computer was churning through millions of possible moves to figure out what's the right move. AlphaGo looks through actually a very small number of moves because it's doing something much more intuitive, and that intuition is driven by having made this into essentially a supervised learning problem, a classification problem, if you will, of looking at a Go board or a chess board and figuring out what's the right move just by kind of intuiting it in the same way that we would of just seeing the right answer. That's effectively what it does.
Yeah. So next, I want to transition a little bit to, as mostly open source developers here who run their own stuff. A lot of the big advances in machine learning has been on cloud platforms, right? So, like, what is the? Yeah, I guess I'm curious your opinions. Should people be trying to do this stuff themselves? I mean, Varun, you do. I don't know if you run how much of what you do you run inside Google's cloud versus doing it locally. I mean, that's a trade-off too. So I'm curious. You know, where do you guys actually run this stuff? You know, where do you see the market going from that perspective? Will there be a big open source market for all this, or is it something that you know, Amazon and Google?
I think it's So for us, one of the things was that we wanted answers quickly, right? So for example, we trained everything, we did it locally, either in our own hardware or like something. Well, we did not need, time was not of the essence. So like we would train for like 8 hours, 16 hours, 17 hours. That was not a problem. The interesting bit was putting these models somewhere and serving them. And when we went live in August last year, one of the things that was a problem for us at that point was that the Golang bindings were not there, so it was in Python, which meant that we had to like serve it, and we needed to like figure out how to serve this correctly. And secondly, like the other part of the problem was that we wanted to like deliver the answer. Like you're starting a call, you want to know like, should I do Wi-Fi 3G, right? And maybe the app was not open, you did not have enough context or time before, and you've started to dial out, right? And now you need an answer before the call's set up to say like, oh, you collect everything, do the checks, and then at the last moment, there's still a possibility to use Wi-Fi or 3G, right? If both succeed. And so we were trying to compress the time, and at that point there was no Amazon stuff at that time, and so we had no choice today to serve it and to like reduce the time and so on and so forth. So we went down that path of doing it ourselves, and of course Google figured this out, produced a bunch of new things in late September. It was not too far from the time we went live, so we dialed it back. But today, I think there's a lot more, and I think in 6 months there'll be a lot more available. So depending on when you go live and what kind of issues you face, I think it's always better to go with something that's already been tried and tested, as opposed to trying to, because a lot of our final AI problems were not AI problems. They were like getting this QA'd and available, globally available, millions of sessions starting at the same time, trying to get a response to them immediately and not crashing and burning, and not making that app crash, right? Because we don't want fate sharing and so on and so forth.
Yeah. So, Michael, I mean, did you see it as your job to run these algorithms on hardware you control, or what's your perspective?
My perspective, it's very early on in what we're doing. So we're only doing research on this and very little production. We're a very small team, so we're producing our own hardware and we're taking orders, and we have a few customers, but their requirements are usually very low powered, so we have absolutely no internet connectivity. And what we're seeing is that our duties in the future will be going into the internet with some limited bridging and gateways. So I have one customer, for example, they're doing long-range radio communication, and this is really only useful if you're communicating these low-power devices running on milliwatts across cities, so you don't have Bluetooth or Wi-Fi, but you are doing small bursts of data, which you could then possibly run over an IP network with a MQTT protocol or something. And that's really where these pattern matching and assisted machine learning frameworks are going to help us maintain security, do the management, and deploy updates. But right now, we're really at the very beginning. So it seems to me that we've got people familiar with theory and a lot of production, and I'm kind of doing the research early on for my domain of work, which is hardware.
Yeah. So, James, I'm curious your perspective. I mean, I know you're going to talk about your company, some of the things you're doing tomorrow, but certainly it seems you're making some bets on how this market will evolve in terms of how will companies and people run their own algorithms locally, or do you see this more in the cloud being controlled by Google and Facebook, and how do you see that playing out?
I mean, at the moment, if it is a classification task, then we will stick it out on Google and use Google APIs because they're extremely good at it. And if it's a decision-making task, some sort of machine language task, then we do that on our servers because it's not so easy to get it. And you get all these sort of problems. The most pathetic and annoying problem is that I started a company called Sen.ai, or Sen Inc., right? If you say Sen Inc. to Google's API, it goes Sin Inc., right? So the problem is, as soon as you use someone else's API, what on earth do you do when it doesn't do the right thing? You can't go go into Google and say, right, retrain it, this is stupid, right? So you lose the ability to resolve very elementary problems like that. Also, for example, we integrated with all of the sort of Amazon Alexa and things. They all reply in 6 seconds, right? We want a human to go, oh, no, that's the wrong answer. You try and decide it's a wrong answer, intervene in something in 6 seconds. Well, so can you change 6 seconds to 8 seconds, which most humans can do? Nope, that's the API you get. So the problem at the moment is that what you get out there is extremely good. You couldn't possibly afford to build something of the quality that they built, and yet very often it's completely useless. So that's the trick.
Yeah. Before we have a couple more minutes left. If there's audience questions, we can take some. Otherwise, I'll keep asking. Go ahead.
Question in the back.
Yeah, I don't know if we have an extra microphone.
Well, we can just repeat the question.
Yeah. Yeah. Please remember to turn it on.
At some point, the discussion, I felt it hanged around having to deal with GPUs and with the codes not being optimized for them and whatnot. And shouldn't we have, or shouldn't there have been mentioned something about the TPU units that Google are using, or the recently launched products from NVIDIA, like the Tesla P100 or DGX?
Well, they keep claiming each time that they bring one of these things out that they've done a 5-year leap ahead of the other one, and 9 months or so later, the other person then launches something that they claim is a 5-year leap ahead, and so on. And as I said, at the moment, if you look under the hood of what they're doing is fairly agricultural. They're just using video imaging technology to do AI. Now they've reduced, Travis is kind of going, well, okay, so they've dropped out that it's no longer floating point. So it's no longer 30-bit, 2-bit floating point, it's 16-bit fixed point, which gets them some considerable speeds. But still, the vast majority of the chip is going to memory and getting things they don't need to get, and then multiplying them by 0, right? So a lot of so I think there's some big leap forwards available.
Yeah, I would add. I mean, I'll let the other panelists comment too. But at least for like the I've been to a couple of sessions on the TPU that Google has, and they've claimed they've done a bunch of optimizations to make it work better and drastically reduce the power they have to do. But it's only for Google Cloud. So the TPU might be better, but if you don't want to use Google Cloud, then it doesn't matter, right? So you're kind of stuck there. Another topic we did talk about a little bit is this idea of edge AI, right? And then pushing a lot of this down to devices. And probably in a similar way that we've seen even with like WebRTC, where you used to have to do everything in the server and everything had to be MCU based. Now you can do an SFU and kind of push a lot of that stuff down. But there's always trade-offs in doing that. It seems it's just emerging, but the idea of being able to run some of these models and doing machine learning on device is starting to happen. And Google certainly pushing that with some of their more advanced phones, and Apple's doing that. They have with AirKit, a lot of the things that they're doing. So if you want to run it, but that sticks you inside those ecosystems, and you're stuck using those.
So one of the things we tried to do similarly, because of Wi-Fi 3G, we thought it was also a localized problem. You do not need to do this in the cloud. But and some of the hardware has come out very recently, like just in the last 6 months. But one of the things that we noticed we had to do was rethink the problem again. So it is like all the stuff that we had already done was not applicable when you do it on the device, because you have to the kind of memory or kind of data that you have, and what you would be capable of doing is totally different. So you would have to rethink about how are you going to train this thing, and how are you going to learn from that. And so there's an opportunity there. The hardware is still at least a year out, but the algorithms, at least in our case, we would have to put in at least again a significant amount of time to redo this if you wanted to move something to the edge.
I'm pretty optimistic on the hardware. I mean, I agree with James that the sparsity is a huge problem right now, that we're just doing a lot of inefficient things there. I think also, as I mentioned, that data movement is a big problem. But hardware moves slow relatively, but it has been taking some big jumps. I mean, the first thing is that, as you pointed out, these were just graphics cards before, but this latest generation of both the TPU and then the Volta architecture by NVIDIA, they focused on making multiply accumulate efficient. And that's where there was a big jump in this last generation, is that they were able to, on Google's side, go to fixed point and then do this fancy pipelining trick, to make multiply efficient really fast. And then NVIDIA did the same thing on their Volta units, or a similar concept, to make a multiply accumulate unit really fast. And so that's the first step, is we know that multiply accumulate is our fundamental primitive now. And so that's going to get baked into the hardware and made really fast. Now we need to focus on data movement and getting over the data movement bottleneck and getting sparsity optimizations in. And there's a whole slew of startups that are working on this. Speaking of open source, which is a principal focus of this conference, the RISC-V architecture, there are a number of companies that are building around RISC-V, and many of them are focused on the artificial intelligence machine learning market and are building chips that extend the RISC-V instruction set with interesting optimizations focused on machine learning that do take into account sparsity and data movement. And you can find some interesting talks about that at the RISC-V conference, where they went through a number of these things. A lot of this stuff is very quiet now, but if you think about how much money is going into these data center deployments for machine learning training, the incentive for startups and new ideas here is huge. It's just that the lead time for hardware is so long that in 2020 or 2021, we're going to see a bunch of things pop up out of nowhere that are being worked on right now. And as mentioned, out on the edge, it's also exciting because that's where a lot of the use cases for these are going to be. If you think about sensors and other small devices that can be out there, if you train a network and then bake it into a device, it can operate super low power, even more efficiently than the traditional von Neumann machines. And so there's going to be a huge explosion of these AI-enabled sensors out on the edge, and there's going to be a lot of opportunity for new hardware innovation there as well.
We're just about out of time. There was one topic on the list I did want to touch on, since most of the audience here is not doing machine learning, but I'm sure they should be, or they should at least be learning about it. Could each of you just say, or give your thoughts, if you have them, on where should people go to learn more about machine learning, particularly on topics or areas that are going to help people with doing things like deploying telephony, open source telephony?
Maybe, I think the TensorFlow tools are great. I think Google does a good job of educating people. They've got a long-term interest in getting people on their platform, and they're doing a great job with tooling and education.
Michael?
Yeah, I have to agree that TensorFlow is a pretty easy framework to get started with. If you're dealing with optics, recognizing optical patterns, then OpenCV is probably very good for this type of crowd with open source.
Yeah, so TensorFlow, of course, like we use it every day. There's all the Python libraries related to not only TensorFlow but AI that they are really good. I think that's a really good place to start.
James, any different thoughts?
I can't add to it. The thing that I've been playing with in the open source world is the IBM quantum computer, right? So that's going to push us to doing stuff in the cloud and not on the edge, because you can't put a dilution refrigerator in your laptop at the moment. And it's worth spending a little bit of time just seeing what's going on there, because at some point it'll suddenly appear as the best way to do classification.
All right. Well, I want to thank you. I know James and Travis, you both have talks tomorrow that cover some of these topics, I think. So come back more for that. Thank you all.
Thank you.
Yeah.
Thank you, Chad.
Thanks.